Okay, so this is 2.6. Let me write this over here. 2.6 modeling with functions day 1. Okay, we're going to spend a couple of days on this. Really, there's not much difference between the 2 days. It's just we thought we really needed to spend 2 days practicing this. So let's just jump into problem or example number 1. So it says a woman 5 feet tall standing near a street lamp that is 12 feet tall, as shown in the figure. Find a function that models the length L of her shadow in terms of her distance D from the base of the lamp. Now, this type of problem you need to get used to, where there's more than one variable, but they're asking you to solve for a specific one. Now, first, let's just see if we can draw any kind of relationship. These should be right triangles because we should have some perpendicularity going on between the woman and the lamppost and the ground. Okay, so if we think about it, we've got similar triangles because of this angle is the same. So we could set up a proportion. So let's set it up as 5 over L, okay, and that should be equivalent to 12 over D. D plus L. All right, and it has to be D plus L because for this larger triangle, you have to consider the whole base of that triangle. Now we're trying to solve for L. This now just becomes algebra work. So maybe you're thinking of cross multiply. It's not a bad idea. 5 times D plus L equals 12L. And if I distribute this 5D plus 5L equals 12L. Let's think about subtracting that 5L over so I can get my L's on one side. Now, sometimes we have to factor, but on this one we really didn't need to. Now, if I'm solving for L, I would now want to divide by 7. All right, so if I divide both sides by 7, I get that L is equal to 5 over 7D. And it might just be a little bit more proper to go ahead and write this as L of D equals 5 over 7. Whoops, that's my fault. There we go. 5 over 7th D. Okay, both of these are fun though. Both of these express the length L in terms of her distance D. Now, anytime you see this in terms of her distance D, I'm not asking you for a number answer, and in fact, you can't come up with one. Now, we actually could do a minimization or a maximization here. They don't ask us to do that though. We'll save that for when they ask us, like on this problem. So number 2 says, a gardener has 140 feet of fencing to fence a rectangular vegetable garden. What is the maximum area she can fence? Now, on your notes, I believe it has parts where it first asked you to define your variables and write an equation for what you're trying to maximize. Now, we're trying to maximize area. So I'm going to say that area equals length times width, okay? And if I draw this picture, okay, you can define it however you want. This can be width, this can be length, all right? So we've got width and length. Really clear here. All right, so part B says, write another equation using the other given information and solve that equation for one variable. So let's use the fact that the perimeter is 140 feet. So that's going to tell us that 2W plus 2L equals 140. Now, we need to solve. Now, it doesn't really matter here if we solve for W or for L. So I'm going to go ahead and solve for W. Okay, first of all, we would have 2W equals, oops, let me back that, 140 minus 2L. So that W equals 70 minus L. Now, we could have just as easily solved for our other variable, L, and we would have gotten 70 minus W. Either way really would be fine, okay? So don't stress out about which one to do. In the end, you have to interpret your answer anyway. Okay, part C says rewrite the equation of the quantity you're trying to maximize in terms of a single variable. So up here, instead of doing L times W, I'm going to do L times 70 minus L. And in order to find the maximum, which is what D is asking you to do, we're going to use our calculator. There are definitely ways to do this without the calculator. For now, we're really going to focus on the calculator. Okay, so in Y1, we're going to plug in X, parentheses, 70 minus X. and we are going to find the maximum point, and then we're going to interpret our answer. Okay, so pause this and get your calculator out if you haven't already. And so we're going to type in 70, or sorry, x, and then 70 minus x. And now let's think about what our window should be. Now, who knows what your window is from the last problem? What do you think the most that x could be? Looking at our equation, what is the maximum number of x? Okay, x can't really be anything more than 70 because if it were, then you'd have a negative side. Now we're looking for the maximum area. So your y max, you're going to have to think about this a little bit more difficult. You're going to, or more complete. You're going to have to really think, okay, what is the maximum area that we could have here? Okay, well, let's say that one of the sides is 70. All right, could the other side be anything much more than that? No. If one side was 70, then the other side actually has to be 0. So it's not that both sides could be 70. So this you can kind of play around with. Let's think about, let's think if the sides were maybe 40 and 40, okay? Then that would give you 1,600. In fact, I'm going to go ahead and short this just a little bit to show you what would happen. Let's go ahead and make that into 1,000, and let's hit graph. Now, if I don't see the top of this parabola, then I can't find the maximum. So even if you don't make that number big enough, that's okay. All right. You have to have somewhere to start, though. You can't just start it at 10. You wouldn't have even known what the graph looked like at all. Okay, and notice that this does hit right here. I'm not concerned about the 0. I'm concerned about the max. So second trace, and then the maximum is 4. And it is going to ask you to do left bound, which we are. And then you're going to have to go all the way to the right. And press enter, enter through the guess. And here we get 35 on the dot, and then 1225 as our actual area. So what's interesting about this problem is if you notice that this is 35 and then 1225. 35 is the length. So the length is 35 and we're in feet. So what would the width be? Well, the width, you think about the fact that these two are going to add up to 70 because all four are going to add up to 140. The width is also 35. So this ended up being a square, which maybe doesn't surprise you too much since we're trying to maximize the area. Okay, the actual maximum area is 1,225 feet. And make sure you're using good units here. That is our final answer. Okay, let's look at the next one. This has to do with another max problem, but talking about money. So it says a hockey team plays in an arena with a seating capacity of 15,000 spectators. With the ticket price set at $14, the average attendance at recent games has been 9,500. A market survey indicates that for each dollar the price is lowered, the average attendance will increase by 1,000 people. Find the ticket price that will maximize revenue from ticket sales. So first, let's define what revenue is. Revenue is not necessarily a profit. It's just the money that you're bringing in. And so we have to really define our variables. It doesn't work us through A, do this, B, do this, C, do this. So we've got to know that those are things that we need to do anyway, or at least think through. So I could let X be the actual ticket price, but when I'm writing my equation for revenue, all right, it's going to be much easier if I can write an expression of ticket price in terms of the number of dollars that I'm lowering. So if you think about it, it says for each dollar the price is lowered, the average attendance will increase by 1,000. So if I let X be the dollars that I'm lowering the price, my problem's going to work out pretty nice. Now, there are other ways to solve this problem. I think this is the most efficient way to solve it. And as I work through this equation, I'll explain to you again why I did that. So let's first think about how we would come up with revenue. We would do whatever the ticket price is This is not necessarily going to be a number, but it's going to be an expression. So the ticket price times the attendance, or the number of tickets, okay? But we'll call this the attendance. Okay, so however much the tickets cost times the number of tickets, that is the revenue. Not necessarily profit, but how much money is coming in. If you have questions about that, please bring them to class. Okay, so the ticket price right now is set at 14, but if I lower it, I'm going to be subtracting however many dollars I lower. Okay, so we're going to let R be, for ticket price, we're going to do 14 minus X. So I have an expression for the ticket price. Now I need an expression for the attendance. Also, that's dependent upon how many dollars that I lower the price, because right now the attendance is 9,500. Okay, but that will actually increase, okay, by 1,000 people for every dollar that the price is lowered. So I'm going to add that to 1,000x, because 1,000x, this will be 1,000 if we lower the price by $1. It'll be 2,000 if I lower the price by $2, and so on. Okay, so maybe you would have had a really hard time coming up with this expression or this equation. But now that you've seen me do it and I've kind of reasoned through it, you can do it the next time. You've just got to take the time to really think through the problem, and setting a convenient x is the first way to do that. All right. We need to now find the maximum. All right, so we're going to go back to our calculator. Not even going to simplify or multiply or anything. I'm going to go on my calculator. I'm going to type that exact thing in, because my calculator knows how to simplify expressions, and it doesn't make the same mistakes that I'm likely to make. Okay, so here we have our revenue. We're trying to maximize this. So again, go to your window, and you've got to set your window right. So I'm going to go to my Xmax. Let's think about what the most number of dollars I could lower the ticket price. That would even make sense. Well, if I'm starting at $14, the most I would do is lower it by 14. Even that is too high, but we'll just go ahead and we need a max, so it's fine if it's higher. Okay, so let's think about what our revenue max would be. Let's think about what the most amount of money we could make. Well, right now we're making, it's $14 times 9,500. I'm going to go ahead and type this in. I'm going to show you what happens. Because again, you don't have to get this perfect on the first time. So whatever this is how much revenue we're making right now. Okay, so then we go, not a second, but we go to graph. And if you notice, I didn't go up high enough, okay? And really, I'm going to take this down to like -1, because I don't need that. Same thing here. It's not that big of a deal, but I really don't need negative numbers for my mins there. Okay, so that wasn't enough. So let's just make this go up higher. I mean, that's ultimately what you can do here. You just need a place to start. Okay? Another way maybe to have found a good logical maximum revenue would be to think about the fact that there's going to be at most 15,000 spectators. And so you could have figured out about how many dollars you'd have to decrease and so on. It's not that big of a deal. You can just do mild increments, increases until you figure it out. Okay, so now let's find the maximum. So I need to move this over to the left. Make sure all the way to the left of the max, and then all the way to the right. And later on, I'm going to show you how to do all this without this maximum feature in your calculator, but for now, this is good. So we get 2.25 and then $138,062.50. So let's write this down first. And then let's interpret our answer. We always got to interpret our answer, because here, X did not represent ticket price. Remember, X was the number of dollars that I lower it. So if I want to find what is the ticket price that gives me this maximum revenue, I've got to subtract $2.25 from my original price, which was 14. So 14 minus 225, that's going to be 1175. And then the maximum revenue, which is what they were also asking. Well, they weren't asking it, but we're going to go ahead and write it. $138,062.50. And notice that I'm using units and everything being very thorough here. Okay, last problem we're going to work together. So this has to do kind of like with a geometry problem, but this is actually more algebra than it is geometry. I've already given you the formulas that you need here. So this is talking about a can, which is a cylinder. A manufacturer makes a metal can that holds a liter of oil, and hopefully I fixed this typo by the time you get a printed copy of it. A liter of oil, and notice that a liter is 1,000 square centimeters. Actually, that really should be cubic too. Maybe I'll fix all this before I printed it off. Let's hope. What radius minimizes the amount of metal used to make the can? What is the minimum surface area? Label your units. Now, this thing right here is the volume. Okay, so let's go ahead and write what we know. 1,000 equals pi r squared h. Now, we know that r is radius and h is height. I can either use this to solve for r or to solve for h. Kind of like in that first problem, I could have solved for w or for l. It doesn't really matter which one you solve for. However, we're going to talk about efficiency. I've got to plug in. So do you want to plug in a somewhat complicated expression 2 times or 1 time? Also, think about the question. It says what radius minimizes. Okay, so I want to have my surface area in terms of r. That will save me a little bit of work. So what we want to do here is solve for h. So h is going to be 1,000, and I'm using 1,000 instead of 1 because I want my radius and height not in terms of some weird increment of liter, but in centimeters. Okay, so we're going to take this and we're going to substitute it in so that my surface area for this particular volume, it wouldn't work for any other volume, but for this volume, I can now have a surface area that isn't in terms of radius and height, but just radius. So instead of writing h here, I'm going to write 1,000 over pi r squared. Now, you could simplify this. You don't have to, all right? But it does create a little bit less writing in your calculator, at least if you cross off the pi's, okay? But we could also even cross off this r with one of these. You didn't have to do that. Your calculator would have known and simplified it for you. This will just create less writing that you have to do in your calculator. So we're trying to actually do the minimum here. That's important. We don't want the maximum surface area, we want the minimum surface area, which makes sense if you're thinking about cost efficiency. Okay, so let's go into our y equals, and let's type this in. So first we have 2, and don't ever type in 3.14 and think that that's good enough. It's not. Always type in the pi button. Okay, plus, now we're going to put this in parentheses. 1,000 divided by x. Excuse me. Okay, so now let's go to our window and let's change this manually. Let's think about what do we think the most r is. I'll think about a liter of anything, like a liter of Coke. I mean, the can be shorter and fatter, but what do you think the most x could be? I'm thinking it would definitely not be more than a foot. That's like way big. Or we're not in inches. That's my fault, but still, we'll say 10 centimeters. I don't know. This is still going to be more than we need. Okay, don't make x max too much, but you don't have to worry about getting it real close to the answer, just enough so that we can see it. Okay, right here, our y max. Let's think about what should our y max be. Okay, here it's surface area. Now, surface area and volume are not the exact same. They are different. But for most things that aren't extreme in nature, like a really, really short fat can or a really, really tall skinny can, they are going to be sort of close to each other. So I'm going to go ahead and just go with 1,000. You could do calculations. It's really not that big of a deal. You're going to know right away if this was enough. All right. The only thing you don't want to do is make that thing too small. All right. So here I see the maximum, or I'm sorry, the minimum. So second trace, min. We're going to go all the way to the left, press enter. We're going to go all the way to the right. And this, you can tell, is not a parabola. It's kind of a mixture between radical and a parabola. And so it is irrational. There is, probably a slant asymptote there. That's really not important for the solving of this problem, though. And so here I have my minimum. Okay, so we write this down, 5.419, comma, 553.581. So it says, what is the radius that minimizes the amount of metal? So the radius, we write out our answer, interpret our answer, is 5.419. And remember, we put everything in centimeters. And the minimum surface area is this other number, because that's what our equation was in terms of. It was for surface area. And remember, surface area is going to have square units. Any kind of area is going to have square. Any kind of volume is going to have cubic. Okay, make sure you put the correct units there. Okay, please bring your questions to class.